Yay! Hello and welcome back! Today we are going to be making a new kind of component. It's going to be a sheet metal component. Here we have a sheet metal folded part. It looks to be made of steel, and I believe it's a bracket for some kind of machine. So we're going to have a look at how to model this thing in Inventor and Fusion 360, and we're also going to do drawings complete with folding diagram numbering, folding instructions. Wonderful. Let's get to it. Okay, so here we have the completed model. This is a sheet metal part defined in Autodesk Inventor. So these not only look the part, but they can also be flat patterned. So here we can say go to flat pattern, and it folds it out flat so that it can be cut out with like a laser or a water jet, most likely a laser. And you can put in your bend numbering, so you know what order the bends occur in. And then you can top it off with a drawing that will show all of that detail on there. So today we're going to have a look at how to do exactly that. All right, so we'll go and begin by starting a new sheet metal IPT file. Lovely. So to start, what we're going to do is we are going to model this bottom plate here. We're going to leave out the slot for the moment, but we'll come back to that later. So we'll come up and we'll click Start 2D Sketch, and we'll model it on the XZ plane, so the ground plane. We'll correct the view, and now we'll take some measurements. So quickly, we can see, yeah, it is 110 long and 34 wide. So we'll put a rectangle here. In the fourth section of the Create panel, we'll come along here and click Rectangle, 2 point. And now we'll click once for the origin, and then again arbitrarily in space. We'll hit Escape, and we'll add our dimensions. So here we can define the length by clicking and clicking again, and we'll say that it was 110 millimeters. And the width here was 34 millimeters. Beautiful. Okay, and we'll click Finish Sketch. Now, if this were a normal 3D model, we'd come along to the 3D Model tab, we'd click Extrude, and away you go. But sheet metal works a little bit differently. In this one, we're going to come to Sheet Metal, and here we can click Sheet Metal Defaults. So this lets us play around with the parameters that govern the actual sheet metal itself. So when using sheet metals in Inventor, unless they're multi-solid body parts, they have a single thickness all the way through. So in this case, it is 1.42. Bizarre. Okay, so underneath sheet metal defaults, we'll untick use thickness from rule, and we'll say 1.42. In truth, this isn't the right way to do it. In reality, we should be editing the sheet metal rules and defining materials and thicknesses and all of these rules here, but another day for all of that. For now, we'll go ahead and we'll put the thickness 1.42. Great. Next, what we're going to do is we're going to define that face. So we'll come and we'll click Face. And here it will automatically pick up on the little profile that we drew. And we can pick which direction it's going into. Honestly, in this one, it doesn't make too big of a difference. We'll click OK. Okay, so we have our fearsome first plate. So what are we going to do next? Let's go ahead and we are going to do this flange that comes upwards here. So we'll start off by defining its height, not including this top portion. And we will say that it is 37 millimeters. Nice. So we'll come along here to flange, and now we'll click this edge here. Beautiful. Okay, so there's lots of things that we can change here. You can change the angle of the flange, you can change its distance, but we will just put it at 90 degrees up and 37 millimeters. So what does the 37 millimeters mean in this context? Depending on what your options are here for the bend position, for the extent, it will change. You click OK, and if we measure, the 37 millimeters will be from this top face here to this lower face down here. Beautiful. Okay, so what's next? What we'd like to do are these little flanges to the side. We'll leave out the little folded hems for now, but we'll put up these side panels. So to do that, super duper easy, we will come along here and say flange and pick this edge, this edge, this edge, and this edge. And as you can see, when it gets to the corner, interesting things happen. Now, how are the corners treated here? As we can see, there's a bit of a 45-degree miter here. We'll also note that this thing is 11.7 tall. So we'll come along here and we'll say the extent is 11.7. Looking good. And as you can see, we've got a miter in there where those flanges meet. Click OK. And it's looking somewhat okay. We'll add in the hems and see how Inventor handles it from there. So we'll come along here to hem. And here we can fold the corners, the edges in on themselves. It's to give it some rigidity as well as make them not so sharp. So here we'll pick a single type hem, and then we'll pick this edge here. Unfortunately, we can't select multiple edges at a time, but that's okay. And for the length, we'll go ahead and quickly measure the length. It's 5 mil, 5.4 mil. So we'll say length 5.4. Excellent. And click OK. Now we're going to repeat the process for the other edges. So we'll come along here, we'll say, we'll come along here and we'll click hem, and we'll click this edge and use the same settings. Click apply, click this edge here, click apply, click this edge here, and click apply. Beautiful. And now we've got our hemmed edges. Now, we've got to be a little bit a stickler for details. I'm not sure if the camera will show it. I'll expand the camera. Hopefully that worked. Hopefully you can see. As you can see, this hem comes further down and this hem has retreated a bit. We want to replicate this in the model because as you can see in the model, the hem is equidistant there. So let's go ahead. We are going to use the 3D model and we are going to use the direct edit tool. A bit of a cheat, but it works well. We'll click direct and we'll pick this face here and this face here. Oops, not that one. Hold down shift to unselect. Or if it doesn't, just repeat the tool. Click direct, click that face there and that face there. And now we're going to click snap to. And now we can pick a point to which we want to extend that face down. So we'll go and click this point here. Excellent, excellent. And now that looks a little bit more true to life. Good, good, good. Okay, so what's next? We've got this top flange. Oh, I'll turn up the camera a bit. We've got this top flange here. Now it comes over the thing and it's also a little bit wider than the rest of it. So let's go ahead and model that. There's actually a few ways of approaching this problem, but I'll show you one way. I'll come along here and click flange, and we'll pick this top edge here, or this one, either or, doesn't make a difference. And now, here we can't click OK because as you can see, a flange that treats this as the top level would suddenly be, clipping these hems. So what we're going to do is change the bend position. So we'll click here. And now we're saying that the bend starts, that this top face represents the bend plus the extent. So there we go. Now we can know that the flange is 15 mil long. So we'll put in 15 mil. Great. And it doesn't have the winglets here, but that's okay. We'll add those in. So we'll click OK. Excellent. All right. So we're going to use some good old fashioned sketches and extrusions, although there's probably more efficient ways of doing that. Here we go, we'll put a sketch on the side, project geometry, and capture this rectangular profile on the side of the flange. We'll do the same on the other side. Here we go. Project geometry, click the side there. And now we'll go ahead and we will extrude these out. And they are 6 mils. So we'll go ahead and click 6 mil there. Hit the little plus to get another extrusion. 6 mil here. And click OK. It's looking pretty good, looking pretty good. Okay, so we are going to add in the slots. So we've got one slot there and a little slot on top. So those are going to be easy. We'll go ahead and do some sketches to make some profiles and then use the cut command. So we're making a rectangle here and quickly measuring. We've got 8 mils and we've got 1.8 and it's recessed 4 mils. Great. So it's 4 mils from that front edge. It's 1.8 mils wide and 8 mils lengthwise. And we're going to use constraints here to align it to the middle there. Looking good. Although 4 mil. Oh, it's true. That's okay. Okay. All right. So we'll go ahead and we'll click finish sketch there. And we are going to use the cut command to extrude this. This works exactly like the extrusion command, except it can go cut along folds and whatnot. Special things in Inventor. Okay, and we are going to make the slot at the bottom. A million ways of achieving this slot, but we're just going to take some measurements. We're going to use a sketch and a slot command. It is 91.25 end to end. So 91.25, 6.4 wide, and 6.8 mil from the end. Okay. So we'll start a 2D sketch on the bottom, and this time we're going to come underneath rectangle and we'll click an overall slot. And I'm just going to put it out in space here for now. So from our measurements, we measured it to be, so this is measuring the diameter, I believe, 6.4 mil diameter. And we'll give it a total length of 91.25, I believe it was. Let's measure. Always measure. 91.25. Great. 91.25. Good. Okay, and the end there, really I should just measure once. 6.8. Great. Okay, so I'm going to drag this approximately into position. I'm going to put this end point here, 6.8 from the bottom, and vertically align it with the part. Beautiful. And click finish sketch, and we will go ahead and use the cut tool to grab that. Awesome. Okay, now there's only one little part that remains, and that's these sharp edges are actually very sharp in real life. So in the real model, they're rounded off. So these are just fillets. I've got 2 mil there, 1 mil at the back, and 3 mil at the front. So we'll go ahead and add in those fillets. So let's go ahead. You could use the regular 3D modeling fillet tool. That works just fine, but we're going to come to sheet metal and click here, corner round. Great. And we will pick, so these are 2 millimeters. So these two here, looking good. The next two are 1 millimeter at the back. And at the front here, we got 3 millimeters. Attention to detail. Look at us. Okay, great, beautiful. All right, so that's the geometry. Good, looking good. All right, we just have to assign a material and do a drawing. So we'll say sheet metal defaults. Here, usually when you're using a sheet metal default, the material gets brought in by that material. So you might have a sheet metal default for, say, 3 millimeter aluminium or 3 millimeter steel or 3 millimeter acrylic or whatever it is that you're folding. And that would bring in its own K factors, bend compensations, that sort of thing. But for this example, we'll just go ahead and we'll choose a material. We're going to choose stainless steel. There we go. And click OK. Good stuff, good stuff. So we'll go ahead and save that before continuing. Always save early and save often. So we'll call this, what are we calling it? Sheet metal rail. Sheet metal rail. Good stuff. Okay, oh, not just the drawing just yet. We need to make a flat pattern and we need to put in some bend order numbers. So to make a flat pattern, the first part is to define an A side. This is the side that's going to stay flat while the rest of it unfolds around it. We'll say define A side, click the bottom here, and then click create flat pattern and keep an eye on the model tree here. See, we've got folded model. And when we click create flat pattern, it will create a flat pattern there. And you can switch between the flat pattern and the folded model by double clicking. So there's the folded model, there's the flat pattern, folded model, flat pattern. Good stuff. So I'll show you some cool things that you can do with this. The first one's bend order annotation. So Inventor tries to take a crack at what order these things should be folded in, but maybe you know better, or maybe you know the limitations of your own machine. So here you can come along and click bend order annotation, and you can overwrite the default values that have been assigned to it. So we might go ahead here and say, let's replace this with 1, and this with 1, and go forth and rename all of the, renumber all of the bends according to how you think they should go. So maybe your next bend would be this one, 2, or maybe that one is 2. I don't know. Mention in the comments. 2. While I did this, it is worth mentioning that no matter what the topic is, something can always look simple, and then you get into the nitty gritty of it, and everything has these dizzying levels of complexity. And sheet metal is no different at all. I promise you that. But very, very fascinating. So if you know anyone with expertise, definitely pick their brains for their knowledge, because it's hard to come by. Okay. All right, so we'll go ahead. We got our bend order numbers. Okay, so we got our flat pattern here, and you know your sheet metal guys asked, we want a DXF so that we can cut this out using a laser. So we'll come along here and we'll right-click flat pattern, and here you can say, where is it? Where have I dropped it? Save copy as? Yes, save copy as. Yeah, lovely. And now you can export it as a DXF file. This is the best thing ever. I'll do that again because it's so good. You right-click the flat pattern, and here you can say save copy as, and then export it as a DXF, sheetmetalrail.dxf. And what is a DXF? If you don't know, it's just basically a 2D drawing in a very, very simple language that can be fed into, say, like a cutter or something like that, or it can be read with AutoCAD. It's very, very open. You click OK, and it'll go off and it'll produce a DXF. Maybe we'll have a look at that a bit later. Okay, so that's it. That's the model. Good stuff. We will go ahead and make a drawing of it. So we'll save that, and we will go and make a drawing. So right-click Folded Model, and click Create Drawing View. And now go ahead and choose your favorite template. Choose metric, ISO.IDW. Click OK. And now what we're going to do is do a drawing in 2 sheets. The first sheet is going to have the folded model. So as it is when it's completed, you know, its overall height, its overall length, its overall width, the thickness of the thing. And the second sheet on the same drawing is going to be the flat pattern with the folds and where the bend lines are and whatnot. So we'll go ahead and we'll place down our drawing. So we'll click on the view cube and click left, and that'll be our first drawing. That'll be our first view. And we'll go ahead and we'll put in some projected views. So we'll click projected, click our base view. There we've got our bottom, there we've got our top, there we've got our front and back, however you like to make drawings. I'm not going to pretend to be a drawing expert. I always found the 3D modeling stuff to be very interesting, and the drawing to be quite a good skill. Something that you have to get good at over time. Okay. It's not knowing how to use the tools. The tools are easy. It's about knowing what to do. Apparently, good drawings have the bare minimum number of dimensions to fully define the thing. Trickier than it sounds. All right, so we're going to, firstly, I like to make the isometric shaded view so that it's a bit easier to see. And because I'm a nice guy, I like to put a second isometric view so that you can see, intuitively understand the thing without having to interpret a drawing. Go ahead and put in our drawing dimensions, annotate, and we'll say dimension. And again, there's a million tools that you can use for drawing. For this video, we're not that interested in the details, but I'll quickly put in the major dimensions so we don't feel too bad. At least we can say we tried to do a drawing. Yeah, very good. And very importantly for this sort of thing, it'd be very useful to have the dimension of thickness, which represents the thickness of the sheet metal. Probably a poor way of doing it, but I'm going to put in some text to say that the material is 1.42 millimeter thick stainless steel. Probably better ways of recording which material you're using. Okay, so that is the folded model, and it's probably worth mentioning down here in your title block that it's the folded model. We want a second sheet, which will have the real stuff. We'll come along and we'll say new sheet, and this is going to be our unfolded model. So we'll click base view again, and we'll come along and click flat pattern. Yeah. Cool. And yep, you can scale it up or down. I like to make it a little bit bigger, 1.5, and then I always forget there's an A3 drawing and it's enormous, but for the video. We'll come along, and now we've got a whole bunch of lines. We can see the cross-section of the thing. So how do we make a bend drawing? You know, how do you say that this is a 90-degree fold? Well, that's easy. We'll come along and we'll say annotate, and come to table and click general. And with this magic, we just need to click the view. It automatically interprets that we want a bend table, and click OK. And ta-da! It shows the bend annotations that we included in the model. So first fold, second folds, third fold, fourth fold, and also the bend angle and the bend radius. Magical! Okay. We'll come along and we'll add in some dimensions. For these unfolded drawings, I generally like to include two things, which is firstly the overall dimensions, because when you hand over a DXF, it's important that that DXF gets scaled properly. And this, you know, includes bend compensations in the material. So if they have this drawing, they can scale that DXF for when they're putting it on their machine. The second one, and very, very importantly, is to dimension where those bend lines go. So we'll put in some dimensions that detail where those bends are relative to some metric. How you do this is up to you, but definitely capture that, or you'll get some angry emails from clients. Go. Good stuff. Wonderful. Excellent. Good. Okay, cool. Okay, those are all the bends, overall dimensions. We're looking pretty good. I might just throw this one over here. Hey, okay. So, not the best drawing in the world, but it has most of the detail that's required to actually make this part, which is pretty nice. So, we'll go ahead and save that, and we will call it sheetmetalrail.idw. If they don't use something like Inventor, it might be worth making a PDF of this drawing so they can open it up. There are many viewers online for, you know, IDWs and DWGs, but if you want to do them as solid, you can always come here, say export as a PDF, make sure that you've chosen all the sheets, click OK, and sheet metal rail. Looking good. We'll come along and we'll see those files. YouTube videos, sheet metal, yeah. And that should be just about done. And ta-da! We've got a completely mediocre but drawing that shows the principles of it. Wonderful. Okay, so we're going to repeat all this time in Fusion 360. So I'll see you shortly.